In this problem, we have a rod that's held up by a string, and then one end of it is touching the floor, and we're assuming here the floor is smooth, so we don't have to worry about any parallel forces of friction happening. There's just a normal force exerted right there. And we're trying to get the normal force, and we're trying to get the tension in the string. So let's draw in our forces. Okay, we've got the normal force pointing straight up, we've got the tension pointing straight up, and then we have, at the center of mass of this thing, we have gravity pulling down with a strength of mg. And then this problem is pretty quick once you figure out all the angles. The angles are really the tricky part. So let's start getting into all the angles. We have to find perpendicular components for these forces. Let me try to clarify here. I'm going to use the contact point with the ground as my rotation axis. And that means the normal force can exert no torque with respect to that axis. But I'm going to have to find perpendicular components of the tension and mg, and that requires a little bit of trigonometry to figure everything out. So I just put in a perpendicular axis through the center of mass, and I'm hoping that this reminds you of the force decompositions that we had to do for ramp problems, where you would decompose the force of gravity into parallel and perpendicular components. And the angle of incline there turned out to be equal to this angle in here. And I'll just rehash the argument if you've forgotten why it's true. Here's an angle theta. I'm putting a force vector in here pointing down, and a perpendicular drawn here. And I'm looking for this angle right here. So the first thing I do is I say, oh, there's a right triangle, and the acute angles must add up to 90 degrees. So this angle right here must be 90 minus theta. And then I notice another 90-degree angle. But look at this angle 90 minus theta and this angle phi. Those add up to 90 degrees. So I can write 90 minus theta plus phi equals 90. Cancel the 90s. And phi is equal to theta. And so I find that this angle is the same as the angle of incline. Okay, once that's worked out, it's not a big deal to find the perpendicular component. It's going to be given by mg times the cosine of that angle. I hope that's also a familiar expression from all those incline problems that we used to do. And then I need to figure out the perpendicular component for the tension over here. So I'm going to put in a perpendicular axis. And if I extend an axis vertically from the bottom of that vector t, I recognize I have exactly the same relationship over here. I have this vertical axis and I have one perpendicular to the stick. And this angle must also be theta right in here. But that means this angle must be theta. And so this component of the tension is a t cosine theta. So finally I can do my torque analysis around that contact point with the ground. So I have the sum of all the torques is 0, or I could say the counterclockwise torques better add up to the same number as the clockwise torques. And so let's see everything that's happening clockwise. That's just our mg cosine theta through a distance of L over 2, half the length of the rod. So I have mg cosine theta, L over 2. And what's going on counterclockwise, that's the tension. So I'm going to have a t cosine theta exerted through the entire length of the rod. And look what happens. The cosine thetas cancel out. The L's cancel out. And I have a t isolated on one side now. And it's just going to be 1/2 mg. Then I'm trying to think of the fastest way to get the normal force. And the easiest thing you can do here is just look at the sum of the forces in the y direction. In other words, all the upward forces better add up to the same number as all the downward forces. And all the upward stuff, that's an n, the normal force, plus the tension. And that better be equal to all the downward forces. That's just mg. And then plugging in that t is mg over 2. I get that the normal force is also mg over 2. And that's it.